Okay, here we go. All right, so last class we were talking about how we can draw lines now using vector equations, and then we talked about planes, right? And with the plane, we went to the traditional equation of a plane. And what we did at the end of class is we found a way of finding the shortest distance between a point and a line. All right, that's what we ended class with. We also now are going to move on. Well, we're still in the same section, 10.5. We are now going to look at trying to find the shortest distance between a point and a plane, a flat sheet. Now, if you're given a point and a plane, that plane does not necessarily have to be flat, like parallel to the XY plane. So that plane that we're talking about can be tilted in any direction. And then you get an arbitrary point, and we're trying to find the shortest distance between those two. And again, that seems like it might be difficult, but thanks to vectors, we can do it pretty easily. So this is the wording of the process, but I'm going to show you visually how this works. So let's say we start with a plane, all right, and a point. Now, that is not the point right there. That's a defect on the board. So there's the point. Okay, so we have some arbitrary point and some arbitrary plane sitting in space. And we want to find the shortest distance. So somehow that has to be given to us, right? This is our given information. So the way we do this is we first find any point we want, okay? We have to find any point that lives on this plane. So if someone were to give you a plane equation, let's just go ahead and write one up here. Like, let's say we have this point, or this plane. That's the equation of a plane, right? And let's say someone gave us a point, 3, -2, 4. So let's just say that's that point and that's this plane. So we start off by finding any point we want on this plane. So how could I find a point on this plane? Just any x, y, and z that make this true, right? So somebody give me a nice, easy point that would live on that plane. 115? Is that what I heard? Is that? Yeah, 111, right? Would work? Okay, so 111 would plug in and get that. There's an infinite number of ordered triples we could do, right? So that's one in particular. So we have this point on this plane, and we have that point. And now what we do is we create a vector that goes from that point on our plane. That doesn't look like it's on the plane, does it? That's a mistake in my code. It's okay. It looks like it's on the plane, doesn't it? So we want to create a vector that goes from here to here. We can do that, right? So what would that vector be? And we're going to call it the vector b here. What would that be for us here in this particular example here? What's that vector b? One from here to here. 2, -3, 3, right? So if we're going from this point to this point, then we're going to basically subtract these coordinates from those coordinates. So that's our vector b. So we create that vector, and then we take a look at the normal vector of the plane. Okay, so remember the normal vector, if someone gives you a plane, there's a unique, not a unique vector, but there's a vector that points orthogonal to the plane, right? And then of course you can stretch it out or flip it and make it point the other direction. But just imagine that we take this normal vector that's on the plane, and we just kind of slide it over here so that it passes through that point. And we're allowed to move that vector around, right? Okay, so what is the normal vector for this plane here, for this particular example? So remember how to get the normal vector? Are you just being quiet? Or? Do you know what it is? Do you know what it is? Yeah? 2, 3, -1. 2, 3, -1. It's just the coefficients of the plane equation. That's all it is. Okay? So the normal vector is just 2, 3, -1. Y'all with me? Yeah. Okay, so we've got this vector b, we've got this vector n, and now just imagine that we take this vector b and we just kind of shift it over. So we slide it over, right? So that they're tail to tail. And then we project this blue onto the red. We've done vector projections, right, before? If we project that blue onto the red, then it's kind of like the shadow being cast is this from here to here. Now, the projection is a vector, isn't it? But we're not interested in the vector, we're actually interested in its length. So this black piece right here, the length of it, how long it is actually the component of which vector onto which vector? The blue one, right? So that's B for us, onto N, the normal vector of the plane. So does everyone see that? If we just do this computation, the component of B onto N, which is really the length of the projection vector, then that will give us the shortest distance between the point and the plane. So it's actually a pretty nice little geometric construction. Would you agree? Yes. All right, so that takes us back up to the formula. So we are going to take the absolute value, because it is possible that you could get, when you look at this formula right here by itself, it's this right here without the absolute value. And so it is possible that our dot product is negative. So we want to take the absolute value so that it gives us a distance as a positive answer. So it's actually a pretty easy computation. I mean, this is more detail than we need. This is the one I like to work with right here. You're just going to dot the two vectors, right? Find the magnitude of that, or absolute value of that, and then just divide it by the magnitude of n. And that is it. All right? So n dot b over n, and then take the absolute value. All right, so let's go ahead and do that for this particular example we have here, right? If we want to find that distance between that plane and that point, all we will do, where is that thing? I'm looking for my dirty rag over here. Okay, here it is. So for this particular problem, if we want to know the distance between that point and that plane, we are going to take the magnitude of the component of b onto n, which is going to be the absolute value of n dot b over the absolute value or the magnitude of n. All right, so let's go ahead and let's dot these two. This is a pretty clean computation, right? Dotting these two vectors, we should get a number, right? And that number should be the number 4, right? We're just multiplying the components. 4, negative 9, negative 3. We're going to take the absolute value of that, and then over the magnitude of n, which is the square root of the sum of the squares of these things. So 4 plus 9 plus 1. Okay? And so up top we get, what's that up there? Negative 8? Negative 8, and we take the absolute value, so 8 over root 14. There we go. And then we could get that as a decimal, or we could just leave it. But that is the shortest distance between that point and that plane. All right? Pretty nice, right? Okay. Let's do another example. But this one will be worded a little bit different. So here, can I erase? Okay. So here we're given two planes, all right? And we're told that they're parallel. Now, how do I know that they're parallel just by looking? How can I tell that these two planes are parallel? Yeah, look at the normal vector. What's the normal vector of plane 1? I'll call it n1. What's the normal vector of plane 1? 1, 1, 1. What's the normal vector of plane 2? 2, 2, 2. And these two vectors are scalar multiples of one another, and therefore they are parallel, right? And if the normals are parallel, that means the planes are parallel. So we have two parallel planes. And we're trying to find the shortest distance between them. So we've got two planes, right? And we're trying to find the shortest distance between them. And most people, well, not most people, a lot of people will make the mistake, look at this problem, and just say like the distance is 15 or something like that. Do y'all see what they're doing? They're just saying, oh, the only difference is these two, so they subtract and they get 15. The problem is these planes don't necessarily have to be flat like this. These could be tilted, right? So you're not just looking like for a difference between anything. These are tilted, so we're trying to somehow use what we just learned. So how are we going to use what we just learned? We just learned how to find the shortest distance between a point and a plane, right? So
select the point from one of the planes.
Yeah, just find any point you want on this plane, all right? And that will be a point, right? And then use the other plane as the plane from the previous problems, and then you have a point in a plane, all right? So from this one, let's grab a point off of this. I'm going to grab it this time. How about 5, 0, 0? I like using zeros when I can, right? That point lives on that plane. So remember, I have like two planes. Let me tilt them a little bit. I don't want to put them like they're flat. Okay, so I have a plane here and I have another plane here. They're parallel to one another. I just found this point right here. It's that point right there, right? So I have a point, and then I have this plane right here, which is this one. So this is plane 1, this is plane 2. So what next? Find a point on this plane, all right? So any point will work. So what's a good point off that plane?
10, 0, 0.
10, 0, 0, okay. 10, 0, 0 is a point on that plane. What is our next step? Connect them, I don't know if that's what I heard, but create a vector, right? That goes from the point on plane 2 up to the point on plane 1. So I want to create this vector here. That vector is, in the formula, that's b, right? So what is b going to be for us? Negative 5, 0, 0. Okay, so we've got b, and then we need the n also, right?
Yes.
And the n we're going to use is going to be the normal off of this plane.
Yeah.
Okay, so the normal vector off of plane 2 is 2, 2, 2. There we go. And that's all we need to do the computation, right? Yes?
Wouldn't matter which plane you do the normal vector off of.
It actually, well, why don't you think about that? Okay? So I think what you're asking is, could you have used the normal vector off of this one, right? So what would change if you did it that way? What would change? You'd be using normal off of this, so that would change.
Yes.
Would b change?
No. Wait. Yes, it would.
Yes, because you'd be going from here to here, right?
Okay.
You need a point off the
Right.
second one.
So you need a point off of which one?
The second.
But this, okay, but this is a point off the second
I'm
one.
saying as your, I mean a vector off the second one, for B.
For b?
You'd be going from 5 to 10. So you'd be going from 1
I'm
to
saying make b go from here to here. So would you change that to positive?
Yeah.
Right? Right? And then aren't you going to just dot these two?
Yes.
Right? And then take a magnitude? So I guess to answer your question, you could do it, right? Doesn't matter which perspective you want to look at this from. I'm going to stick with this though, all right? So our distance, okay, the shortest distance, I'm going to call it little d, should be equal to the component of b onto n, which, oh, absolute value of that, which will be this over this. Okay, let's do the dot product. So dotting these, negative 10, 0, 0, so negative 10 on top. On the bottom, we're going to get the absolute value of 2, 2, 2, right? Square each one. So 4, 4, 4, root 12. So this is going to be 10 over root 12. Okay? We're good? Now, there are some really tough problems that we can do now that I'd like to present to you here. There's a few of these like in your homework. Let me bring them up real quick. Might be able to get to them faster this way. What is this, 10.5? Just had them here. Let me go back here. I just had them a second ago. There we go. So here are some things now that we should be able to do. All right? So first, in terms of finding vector equations of lines, if somebody, we should be able to find the vector equation of a line if someone gives us 2 points. So if I gave you 2 points right now, you should be able to give me the vector equation of the line going through those 2 points. You should be able to find the vector equation of a line through a given point, but parallel to some other line. You should be able to find the vector equation of a line through a given point and perpendicular to a plane. Let's look at that. So, yeah, let's say I ask you to find the equation, vector equation, of the line that goes through, let's say, the point 4, -1, 2, which is perpendicular to x minus 3y plus 4z equals 1. Find the equation of the line that goes through this point but is perpendicular to this plane. All right, so let's try and visualize this. I'll draw it first. We have a point that's given, right? This is the point 4, -1, 2. And we're given some plane here, right? That's our plane. And we are trying to find the equation of the line that goes through that point but is perpendicular to that plane. So let me try it this way. Point, plane, all right? Trying to find the vector equation of the line that goes through this point that is perpendicular to this plane, right? So do you want to hold that? Just hold it like that. You held last time, right? You were real good at it too. You're welcome. Okay, so let's think about this. Point, plane, line through this point can be anywhere, right? But I've got to be perpendicular to this plane, which means I have to point, what? See, kind of like that, right? So, okay, thank you. Good job. Good job. So what does that mean? Like for the vector equation of the line, what are the 2 things I need? For if the general form of a line, vector equation is this, right? We talked about this. Okay, what was this? What did R naught, where did that come from? That's like yeah, it's a point. We're going to take a point and convert it to a vector.
Yes.
So this basically says I need to know a point on the line. We have that, don't we?
Yes.
All we really need then is the direction of that line, the direction vector. But if we have to be perpendicular to this plane,
It would just be the normal vector.
then we could use the normal vector of the plane as our direction, right? So all we have to do here to come up with our vector equation is first get this, which we can convert that to a vector, 4, -1, 2, plus t times, now v is our direction vector, but again, because we have to be perpendicular to the plane, I can use what here for my direction vector?
Coefficients?
Coefficients. So 1, -3, 4. There you go. Right? Coefficients of this. And then we can put it all together. This would be 4 plus t, -1 minus 3t, 2 plus 4t. And that's it. So if we draw this, right, if we just start letting t go through all real numbers, this will draw us a line. It should shoot through that point, and it should be perpendicular to that plane. Questions? So what if I change this to parallel? So we have the same plane here, right? We have the point, and now we need to be parallel, right? Would you all agree that to be parallel to that plane, there's an infinite number of lines?
Yeah.
Yes.
So that would be a bad question, because there's not a unique answer. But if I say you have to be perpendicular to that plane, there is only one answer.
Yes.
Okay? All right, so it's that's not a subtle thing. That's a major thing that's perpendicular. Okay, let's look at another set of problems that another problem that we should be able to do. We just did part C, right?
Yes.
Okay, so let's see D. Find the vector equation of a line of intersection of two planes. So we did that in class. I gave you two planes, right? We gave you two planes, and we found the line of intersection. Do we need to go back through one of those, or you feel comfortable?
Personally, I recommend going back through.
You want to go through it?
Yeah.
I can do one of those.
Yeah.
Okay. So this, to me, part D, is like a fundamental part of this. Like you should be able to find the line of intersection of two planes just like asking someone 2 + 2. I mean, that's what it should be like for a Cal 3 student. It's a basic concept. So let's make sure we can do it, all right? Maybe not 2 + 2, but you get what I'm saying. This should not be a stretch. So let me just give you two arbitrary planes. Negative 2x plus y minus 3z equals 4. And then x minus 4y plus z equals, let's go with 10. Okay, so I'm giving you two planes. Are they parallel? Are these planes parallel? No, they're not parallel because they have different the normal vectors are not scalar multiples. So if they're not parallel, then they should intersect one another somewhere, right? And where they intersect, it should be a line. So we're trying to find the vector equation of that line. So find the vector equation of line of intersection. All right, so we'll go back to the fundamental idea again. If you're trying to find the vector equation of a line, eventually you've got to get to this, right? When I was in school, when I took this calculus as a student, the formula that we used was different than this. The book did something like u of t equals, it was like u naught plus tv. They just used a different variable other than r. And so I can remember my professor telling me to remember this. He said that's the couch potato formula. U plus a TV, right? U plus a TV is couch potato. So I've always remembered it that way, but that's not the way this book presents it. They use R and R naught. But it's basically a vector U plus T times some vector V. So we're trying to get to this, right? We're trying to somehow get these two pieces, really, right? We just have two things we have to figure out. So what about R naught? R naught comes from a point on the line, right?
Yes.
And so any point on this line must live on both planes. So you just have to find an x, y, and z that satisfy these simultaneously.
And then we can do substitution or elimination in order to find.
Yeah, to do that, you just need to solve this system, right? So maybe, how would you go about that if you have two equations but three unknowns? You should probably just fix one of the variables.
Yes.
So I like to kill off one of them. So let's let z be 0. Okay, so I'm going to let z be 0. So right now I'm going after R naught. So I'm going to let z be 0. And when I do that, I get negative 2x plus y equals 4. And then x minus 4y equals 10. That's what happens when I let z be 0. And here's my system of equations. Now I've got two unknowns, two equations. I'm going to do elimination. So I'll multiply this equation by 2. That gives me a new system. I'm eliminating the x's, right?
Yes.
Okay, so 2x minus 8y equals 20. Now I should be able to add straight down. So negative 7y equals 24. And that means y is negative 24 over 7. There we go. So I made up this problem on the fly, so our numbers aren't going to be nice. I can pretty much guarantee that, all right? So that's our y. Once we know what y is, we go back and get z. I mean, right? No, sorry, not z. We go back and get x. We know what z is. Z is 0. So where do we go and plug this in? Any of these, right? Any of these that have x and y. So I think I'm going to do this one right there because that one is the cleanest to me. Like that one, x is like right there. Okay, so using that, plugging back in. For this, I'm going to get x minus 4 times y, but y was negative 24 over 7, and that must equal 10. And so my numbers aren't going to be very pretty here, but x plus, what's that, 96/7 equals 10, and then finally I'll subtract 96/7 from both sides. So that gives me x is equal to 70/7 minus 96/7. So we've got a common denominator. What do we got? Negative 26 over 7. All right, so there. We have a point, right? And that's going to allow me to get my R naught. So let me go ahead and put that down here. The point that I'm going to be having that lives on, one point that lives on the line of intersection is the point negative 26 over 7, negative 24 over 7, and 0. Okay, now how are we going to get v? How do we get the direction vector for this line of intersection? This is the key part right here. So if you have two planes that intersect one another, right? That line of intersection, there's something special about it. There's a way you can get it. There's a way you can get that direction. Yes, so this is hard to draw it, but here's one plane. Let's say that's the line of intersection of another plane through it. Right? So they hit in this line. Terrible. It's hard to draw three-dimensional space on two-dimensional sheet, but there they are. So what we could do is we could take the normal vector, take the two normal vectors, so take this normal vector, and then take the normal of this one. I drew it terribly, so it's not going to look right, but take the normal vector of this one. And when we cross those two, we should get a vector that comes out in the same direction. So let's do this again. So here's one plane, here's the other one, you mind? All right, so if I take this normal vector, if I take those two and put them tail to tail, they're like this. If I cross them, I'm going to get something that comes out right-hand rule like this, and that will be the same direction as that line, right? Okay, so what are the normal vectors I'm going to be crossing here? So my v here is going to be what? Negative 2, 1, negative 3, crossed with 1, negative 4, 1. Okay, so I've got to cross those two vectors. That gives me my direction vector of my line. And crossing was a little more involved, right, than dotting. So actually, I like to write them vertically. How many of you are aware that if you have a pretty fancy calculator, you can do cross products on your calculators? Like if you have a relatively modern graphing calculator, it'll have a cross product built in, or you could even write your own program. Just go Google cross product code for TI-89 or TI-80 whatever, and you can program your own computer to do cross products. All right, so there we go. Let's do it. And we're going to get a vector, right? So what do we get from that first piece? What's that?
13.
Is it 13?
1 minus negative 12.
This and this is going to be positive 12 though,
Yeah.
right? But then we're subtracting it.
Negative.
So 1 minus 12, negative 11? Okay, so negative 11 here. And we cover up the middle one. Negative 2, take away negative 3, so that's negative 2 plus 3, that's 1. But then it's the middle one, so it becomes the opposite. So negative 1. And then we do the last one, which is 8, take away 1, right? So 7. So that's our V. So we're ready. We'll have the vector equation now of the line. So R of t will be the point converted to a vector. Is that cross product right? Are y'all okay with that? Going through kind of quick up here. No objections? There we go. That's it. And then we could put these together. We could put it together, right? I'm just going to leave it here. So if we were to draw that line, it should run right through the intersection of those two planes. More? Brought up the wrong thing. Look at part E. Find the vector equation of the line through a given point in parallel to a given plane and perpendicular to a given line. What? All right. Find the vector equation of a line that goes through a given point. Okay, so give you a point, right? So all you need is a direction vector then, right? But the line we're looking for is parallel to some plane. Now we already said that if you're parallel to a plane, there's an infinite number of answers. But you also have to be perpendicular to a given line.
Wait, is it the same given line that's already?
Nope.
No, okay, it's different.
Yeah, so let's try and put our heads around this. We have a point, right? Let's just say this is our point, it's given to us. And we're given a plane, right? So the line we're looking for has to be parallel to this plane. So we just talked about how there's an infinite number of answers, right? But not only do we have to be parallel to this plane, we also have to be perpendicular to some given line. So let's just put the plane on the back burner for now. Point, we're trying to find this line, right? And we have some other lines sitting here. Where's the ruler? There it is. We have some other, do you mind holding the line? Thank you. Okay, so we have our point. Our line has to be perpendicular to this line, right? So just think about what it would mean to be perpendicular to this line. That means we would have to be like this, yes? But wouldn't any of these work? Like imagine wrapping around this. Any line that did this would be perpendicular. Yes? So aren't there an infinite number of answers here? Okay, so if we look at just the point in the plane, there's an infinite number of answers. If we look at just the point in the line, there's an infinite number of answers. But somehow that and that together give us a unique answer, right? So if you don't mind holding there just for a second, let's think about this. The direction of our line must be perpendicular to this, right? So that means it must be perpendicular to the what of this line? The direction of our line must be perpendicular to the direction of that line, right? So the V we're looking for has to be orthogonal to this V, right? Okay, but we have to be parallel to this plane, which means the direction of our line has to be what to this plane? Parallel to the plane, but what is that? Orthogonal to that normal, right? So okay, thank you. So the direction vector we are looking for must be orthogonal to that normal and orthogonal to that line's direction. So how do we get it?
The intersection of the two planes.
We only have one plane. Is one plane?
But that makes an infinite amount of any.
That's right. This is an infinite.
Isn't that okay?
It is a plane, but we're looking for these shouldn't. There is a plane, right, that this line could live on, But this plane that this would live on would never intersect this plane, right? Because they'd be parallel.
What's the intersection of that plane
With this line? Perhaps. I want you to just kind of take a step back. We are looking for V, right? We are looking for a V. And there are two things that this V must be. Orthogonal to that normal and orthogonal to the direction of this line, right? So let's try and rephrase that. You are looking for a vector that is orthogonal to two other vectors, right? Cross product. There you go. Right? If I take this normal vector and I take the direction vector of this line, whatever they are, and cross them, what does it give me? A vector that is orthogonal to both. Well, shit, that's what we're looking for, a vector that is orthogonal to both, right? So that will work. Does that make sense? Okay. So this problem right here, I actually don't normally go through this problem in class. I'm just trying to show you like the extent of how much I'm expecting you are going to extrapolate on your own. Does that make sense? Like, all I give you is the foundation. Now you have to go kind of take it to the next step. Like, what are you looking for? You know, oh, wait, to cross them, we'll get what we want, right? Okay, so I think I'm gonna leave that one to you. Or I'm just, if it comes up in the homework or in the take-home test, you'll kind of know what to do with it, hopefully. All right, that's stuff that you should be able to do with lines. Now let's talk about planes. You should be able to find the equation of a plane through a given point and perpendicular to a given line. See if we can talk through this. We're trying to find the equation of a plane, right? That's going through a given point. So I give you a point and I say find the equation of a plane that goes through that point. So right now there's an infinite number of planes, right? But if you have to be perpendicular to a given line, right? So if you have to be perpendicular to this line, let's put this line like this. Here's your point and your plane. Then to be perpendicular to this line means I have to be like, here I'll help. I have to be what? Let's see, if I put these perpendicular like that, what do you see as a relationship? The normal vector of this is parallel to the direction vector of this, right?
Yes.
So if I give you a point and I say find the equation of the plane that is perpendicular to this, then all you need is the normal of this plane, which you could use what? For the normal of this plane. What could you use? Use the V, the direction vector of this line, right? So this one I think I can do pretty quickly, so I'll do this one. So find equation of the plane through the point 5, -1, 2, which is perpendicular to r of t equals 1 minus t for 5 plus 2t. So I give you a point, and I give you a line. I say, give me the equation of a plane that goes through that point and must run perpendicular to this. So when I'm doing problems like this, I always sit there and go, okay, what am I looking for? The equation of a plane, right? That's what I'm looking for. Well, what's the equation of a plane? I write it down. It's this. That's the general equation of a plane right there. So what is x naught, y naught, z naught in this equation? Any point on the plane, right? Which I actually have, like that was given to me, right? So I have x naught, y naught, z naught. That's already there, right? So all I have to figure out is what's a, b, c. But remember, the a, the b, and the c is the normal vector of the plane. But we just said that in order to be perpendicular to this line, I should just use the direction vector of this line as the normal vector of that plane, and they will point, the normal of the plane will point in the same direction as the line, and therefore the plane will be orthogonal to the line.
And so you
Could
use
you-
the coefficient of t or
Yeah, so what is the direction vector of this right here? What is our direction vector for this line? -1, 0, 2, right? So I should use that as my normal vector over here. And therefore, this will become -1, 0, and 2. Make sense? So I'll just finish it up. -1, x minus 5, plus, I'll put 0, it's not going to matter. Y plus 1, and then plus 2, z minus 2 equals 0. And then you can just clean it up, distribute, and that's the equation of your plane. All right? Is this helping going through these?
yes.
Okay. Let's look at another one. Did I leave that long enough? Are you all right? Can I keep going? Okay, that was G, right? Oh no, that was F. Look at G. Let's look at G here. So find the equation of a plane through a given point. So again, you're given a point, right? But you have to be parallel to another plane. So this time you have to be parallel to another plane. So I already give you the point, right? So all you need is what? The normal vector, right, for this plane? But you have to be parallel to this given plane. So what can you use for the normal for this? The same normal as that plane, right? And you're done. So that one is, I think, a little easier to visualize, yeah? Okay, what about H? Find the equation of the plane containing a given line and perpendicular to a given plane. Yes?
What do you mean by containing a given line?
So you're trying to find the equation of a plane,
Yes.
right? That contains a given line. That means that I'm going to give you a line, right? And I'm telling you that that line is contained within the plane. So that line goes like this, right? So right now, if I told you this, there are still an infinite number of planes that would satisfy this, because I could just spin this along that plane, that it would be like an axis of rotation, and all of these planes would be satisfied. So right now, giving me just the direction, just a line contained within the plane is not enough. But you also have to be perpendicular to another given plane. So now, let's say there's this plane on the ground, right? And let's put its normal vector here. So that's given, right? The line is given, and you're trying to figure out the plane that is containing that line, that contains that line, but at the same time is what? Perpendicular to that? So how am I going to do that? Where is it? Where is it? So how do I make it perpendicular? Like, I'm going to move it over here so you can see it. Like, when am I going to be perpendicular to this plane? When the normal vector here is parallel to this plane, right? Then I will be orthogonal, right? Okay, so what do? How am I going to get the equation of this plane? This is what it looks like, but how am I going to get the equation of this? All I'm giving you is the line, right? So what do we need to find the equation of a plane? There's two things we need for the equation of a plane. A point. Could you get me a point on that line? Yeah, you could just plug any value of t in, and right, if I gave you the equation, and you could give me a point. Okay, so we have a point. So all you need now is the normal vector. So how are you going to get me this vector right here? How are you going to get that for me?
You're going to cross the normal and the vector.
Good. So this blue is given, right? Since it's given, I know the direction vector for this blue line, right? I know its direction vector. And I know this vector is the normal, right? So if I bring that up here like this, if I cross these two, right, I'm going to get a vector that's coming out of the plane. And that can be the normal of what I'm looking for, all right? Good. So Yeah, I think I'll leave that to you. All right, I'll leave that to you. How about I? Find the equation of the plane through 3 given points. We did that in class. So you give 3 points, find the equation of plane, you just find 2 vectors, cross them, that'll give you your normal. Find the equation of plane through a given point and containing a given line. Ooh, that one's a little different. So this time, same thing, it contains a line. So there's an infinite number, right? Yes. But I'm also giving you a point that's not on this line. So, like imagine that point's here. I have to rotate this plane to get to that point. So now that point's, so I have a line in a plane and a point in a plane. So how are you going to get the normal from this?
Can't you connect them?
Yeah, I can just grab a point off this line, make a vector, and then I can take the direction vector of this line and cross those two, and I get a vector coming out. All right, so all of these things, again, are things that with what we've been talking about, you should be able to somehow extrapolate. It may take some time, you sitting there holding things and, you know, or you just, maybe you can just do it all in your head, I don't know. All right. What's that first mini exam look like? Yeah, I forgot. Let me look at it real quick. Just wondering what from there. I don't think there's anything on here. Oh, wait. Yeah, look at number 6. Find the vector equation of the line. Boom. At that point right there, what are you looking for?
The vector equation of the line.
Yes, but what does that mean? The couch potato formula, right? You need an R naught, which basically is any point on the line converted to a vector, and you need the direction vector of the line. Those are the 2 things. So right away, you know you're looking for 2 things, right? Okay, find the vector equation of the line that passes through the center of this sphere. So your line has to go through that sphere, right? Through the center?
Yes.
Okay, so what is that going to give you if you can figure out the center of that sphere? It's a point on your line, so that's like your R naught, right?
Yes.
And not only does this line have to pass through the center of that sphere, the point, wait, hold on, let me step back. Find the vector equation of the line passing through the center of the sphere and also through the point of intersection of this line with this plane. Okay, so you've got a sphere and you've got its center. Your line has to go through that. Then over here you've got a plane. You've got a plane and a line punching through it. Okay, your line has to go through that point in the center of the sphere.
Oh.
So, yeah, I'm not going to give you any more. But I'm trying to get you to see, like, I'm not going to do anything like this in class. You're going to have to, like, be able to put this all together. Does that make sense? Okay, so see how that goes. I think the others are a little more straightforward. Yeah. Okay. We're moving on to the next section. Yeah, that I believe concludes 10.5. We did that, and then we had already found the shortest distance between a point and a line. And yeah, that's it. Okay. So we're moving on to 10.6. Wait a minute, did I? Yeah, there it is. 10.6. Cylinders and quadratic surfaces. So I'm going to tell you right now, this is a very kind of dry, very, I hate going through this section, but we're going to do it. I'm going to turn the lights down so you can sleep if you need to. No, I'm kidding.
Really?
It's just so you can see the visual stuff here. All right, so here's the idea. Later on in this class, what we're going to be doing is we're going to be looking at these surfaces, and we're going to be trying to find like surface areas of surfaces, and we're going to be trying to find, you know, things like flux. And we first need to be familiar with what these things are. Like when we see the equation, we should be like, oh yeah, that's a blah. And so it's kind of like when you go back and you look at some things that you've already dealt with. Like when you see this equation, x squared plus y squared equals r squared, in two-dimensional space, we all know that that's a circle, right? So if you change r, then you get these circles, right? So anytime we have a variable squared plus a variable squared equals a constant squared, we know that that's a circle in two-dimensional space. All right? In two-dimensional space, when we see an equation that looks like this, variable squared over number squared plus variable squared over number squared equals 1, then we should recognize that as an ellipse. And so as you change the numbers underneath these two variables, it changes the shape of your ellipse, right? So you can have an ellipse that's very wide or taller than it is wide, right? And the shape of this ellipse is all dictated by these two numbers right here, all right? So these are equations we should be familiar with. And then if we change that plus sign to a minus sign but leave everything else the same, then now instead of having an ellipse, we have a hyperbola in two-dimensional space. All right, so we should be familiar with this. Now, what we're interested in is not equations in two-dimensional space, but in three-dimensional space. We want to be able to look at an equation and go, oh yeah, that looks like a whatever it is. We've already seen one, the equation of a sphere, right? The equation of a sphere was first day of class, x minus h quantity squared plus y minus k quantity squared plus c minus l quantity squared equals r squared was the equation of a sphere centered at HKL. Sorry, that's what it was, right? So now we want to look at other equations and be able to recognize them, all right? And the way we do this to draw them is by using these things called trace curves. And I'll tell you right now that trace curves kind of suck because they're tedious. So I'm not going to do a lot of trace curves. I'm going to show you how it's done, but really we're just going to use computer visualization to kind of get an idea of what's going on. All right, so we're going to start off. Our first surface is something you've heard of, and that's a cylinder. All right? Now, it says here traces are circles and lines. I'll explain that in a second. Let me give you the equation of a cylinder. I'm just going to give you an example first. So, a cylinder, your first example, x squared plus y squared equals 4. And the important thing is to understand that we are in R3. We are now in three-dimensional space. So you might look at that right now and you may say, hey, that's a circle radius 2, right? But we're in three-dimensional space right now. We're not in two-dimensional space. So what we're going to do is we're going to try and draw this thing by hand. Okay, so let's do x, let's do y, let's do z. This is our right-hand rule. And so now we do these things called traces. And to do traces, what we do is we fix one of our variables to be constant. And then we try and figure out what the shape is that we're looking at. So I'm gonna fix a variable to be constant right now. You ready? Here it comes. This is my first trace curve. Let z be 0. Okay, well, wait a minute. Hold on. Z's not in here, is it? Z's not even in here. But what I'm saying is, if I fix z to be 0, doesn't that put me on the ground, on the xy plane? Okay, so if z is 0, then draw me what this is. So it's going to be a circle of radius 2 in the xy plane. So I have a circle on the ground here, like that, radius 2, right? And that corresponds, I'm going to call this T1. That's my first trace. This will be T1, okay? So far that's what I know it looks like. Now I'm going to change my variable now and do a second trace. For this trace, I'm going to let z be 1. So z equals 1 means I'm coming up 1 unit off the ground, right? And then I'm going to see how that changes this and draw again. But it doesn't change it, does it? I'm still going to draw another circle of radius 2, but now it's up off the ground 1 unit. So I come up 1 and I draw another one. It's kind of hovering above it, right? And I can keep doing this, right? Another trace. Let's let z be, I don't know, 5, right? And now we've moved up quite a bit. I have another trace up here like that. But I could have done this for any z, right? All z's. And I would have created this right? This beer can kind of thing, right? Infinitely going in both directions forever. So do you see why it says here traces are circles? We have all these circles, right? But why does it say that they're also lines? Well, let's look at some other traces. Does this concept make sense? Okay, so let's look at another concept. Why don't we do a fourth trace where instead of messing with the z, let's mess with one of the other variables. So what if we let y be 0? What would happen if y is 0? Then we get the equation x squared equals 4, right? Which means x is equal to plus or minus 2. Yes?
Yeah.
So think about this. If we do this, right, what we're looking at here is, think of all the points that would satisfy this. Y is 0, right? X is 2, or x is negative 2 and y is 0. What about z, though? What about z, though? Z is not in here, right? So z can be anything we want it to be. Z is whatever we want z to be. We call this a free variable. Okay, it's free to be whatever we want. So think about you going out, let's go to this first point, 2, 0. So 2 on the x-axis, 0 on the y, right? So none of this. And then what about my z? Can be whatever I want, right? So imagine I have to be right here, but my z can be anything I want up and down. So wouldn't that just draw me a straight line up and down? And then if I do x is negative 2 on the other side, that'd be here, I draw it up and down and go like that. Make sense? I could have done this same exact process with x being 0. If x was 0, I'd have y as plus or minus 2, and then these would flip over, and that would give you something that looks like, you know, y is 2, we go up and down, z is free, and then y in the back. And so do you see that those traces are vertical lines? And so a cylinder is a three-dimensional surface where traces are circles or lines. Yeah. I don't expect that you're going to do all the traces to see what all these look like. I just want you to see how traces work, okay? The way I would look at this is I would say, well, I'm going to show you in the notes here. Look, before computers and visualization, you know, before we had all these tools, you know, that you can just go online and graph these things three-dimensionally, you had to do this by hand, right? So it was kind of a pain in the butt. So here's your standard cylinder. So this is x squared plus y squared equals some constant squared where z is free. Anytime you have an equation that looks like that in three-dimensional space, you're going to get this infinite cylinder. And notice that the cylinder opens, we'll say that this cylinder opens up and down the z-axis. Do you all agree with that? Does that language make sense? And notice that it opens up and down the axis that is free, right? So you just have a bunch of circles that go up and down the z-axis. And if we did traces, what we're actually doing is when we let z be a constant, we're just kind of figuring out, like when I started out and I said my first trace, I said z was 0. I just intersected this shape with the xy plane. Oops. Why are they not showing up? Okay. Well, you can see this. You can see the circles, right? Not quite sure why they're not showing up. Here's my vertical traces. Where is it? There it is. Okay, so here's me cutting it with vertical planes. And you can see it hitting in lines. Is that all right? Okay. Just trying to figure out where the heck. All right, it's going to come up in the next example. So we're not going to do that one. So look at this one. This is a different cylinder. This time, look at the two variables that are in the equation, right? X and z this time. Y is free. Y doesn't appear here, so it's going to open down the y-axis. All right? Any equation like that in three-dimensional space will be a cylinder. And there are traces. You can see the circles. Oh, you can see the circular traces this way.